Hello, tell me, has your pickle ever been tickled while you were attempting to understand why code written in different languages were ultimately able to achieve the same results? Well, in today's video, we'll be answering that question and more. We'll also be answering what is an assembler, what is a compiler, and what are the differences between an assembler and a compiler. However, before we answer any of these questions, we have to take a few steps back and ask the far more archaic question of what is the language of a computer? And I'm not referring to the language that you write on the screen, such as in this case, English characters. Nope. I mean, how is data stored in a computer? When I hit a key on the keyboard, such as Q, Q appears on the screen. But how is Q actually stored within the computer? Well, a computer is an electronic device, and therefore electronic signals are used within the computer to process information. And there are two types of signals. There are two types of electronic signals, that being analog and digital. Analog signals are continuous, they are varying waveforms used to represent data such as sounds. And typically, they'll start off at some initial point, say 0. They'll go up to some maximum, say 1. And they will continue in that way for a while, until that data has been completely exhausted. And yes, this is my best drawing skills. And let's end it there. And that continues until whenever. And the second type is digital. Now, digital signals are far simpler. Digital signals are simply represented with sequences of zeros and ones. Typically, a 0 is a low voltage and a 1 is a high voltage signal. Now, again, within a computer, electronic signals are processed, and there are two types, analog and digital. Therefore, digital signals are processed within a computer. And a computer is simply a machine. And the language of a computer is aptly named machine language. May also be called computer language. And you can probably infer from my earlier remarks that machine language is simply a sequence of zeros and SEQU, sequence of zeros and ones. We refer to 0 and 1. So let me take another one. Let's go here. 2 and say we more on 0 and 1s. We refer to 0 and 1 as binary digits. You may be familiar with the more colloquial term of bit. Simply put, a binary digit and a bit are equivalent. Now, if given a sequence such as 0001, we call this a binary code or a binary number, maybe a binary sequence. And it just happens to be that the binary code 001 is equivalent to the decimal system's 1. Here is something that's good to know. 1, 2, 3, 4, 5, 6, 7. Let's do that again. 1, 2, 3, 4, 5, 6, 7, 8 bits is equivalent to 1 byte. 8 bits, so again, 8 bits is equivalent to 1 byte. It doesn't have to be a sequence of zeros, doesn't have to be a sequence of ones. It just has to be a sequence of length 8 consisting only of binary digits 0 and or 1s. Now, take a few moments and look at your keyboard. Look closely, look deeply. Every letter, every number, and in fact every character that you see on your keyboard has a unique binary representation. Even these weird signs such as these god-awful things. Let's do that one, and let's do cool. There we go. Even that has a unique binary representation. Now, it does not end there. Every sequence of characters also has a unique representation. Therefore, something such as hello world will have a unique binary representation. Where do we get this representation from? Well, there are many places and many schemes that create binary representations. The most common, however, is called ASCII, which stands for American Standard for Code, no, American Standard Code for Information Interchange. It is an encoding scheme. And what is an encoding scheme? Well, to encode means to take some input, so input fed into some encoding scheme, which purpose is to transform, and produce output such that the output retains all the original input's meaning and usefulness, while allowing this output to be processed and understood by different types of systems. And that is encoding. Now, we have to explore the evolution of programming languages. Interesting, right? Before we answer any question that we set off to answer, we have to first explore so many different things. So, remember, the language of a computer, which is a machine, is called machine language. It is the most basic. Program instructions are provided in bits. What's a bit? A bit is a binary digit. What is a binary digit? A binary digit is a digital signal that can only be 0 or 1. 0 is low voltage, 1 is high voltage. Now, computers do the same thing, regardless of what computer it is. Let's say that I build a computer, and let's call it computer A, and you build a computer, and let's call it computer B. And fundamentally, I don't want autocorrect, fundamentally, both of these computers do the same thing, right? However, us as computer designers may design the binary code to represent and perform operations differently. Now, before I was rudely interrupted by my own sinus, I was saying that us, you and I, as designers of our computer, may design the binary code to represent and perform operations differently. So I may say that the operation AND is represented by, say, 1010. You may say AND is represented by the binary code 111. So as we can see, the machine language of one computer may not be the same as another computer. And before we move forward, let me make sure I'm recording. Great. Now, there is one thing common, consistent amongst computers, and that is the following. Must store and manipulate data as binary codes. This is a must. Now stick with me. We are getting closer to answering our earlier questions. Early programs, or should I say early computers were programmed in machine language, which makes sense. It's the language of the computer. So say, for example, we wanted to compute the area of some 2D shape such as a rectangle or a square. Well, we know that the area is equal to length times width, given by any basic mathematical formula. So to calculate the area of some 2D shape, square, rectangle, we would need a few more things on a computer. We would need to know that some binary representation such as 100 means to load data. The binary representation, say 100 means to multiply data, so multiplication on data. And let's say we also know that 1000 is same as storing data. Store data. Now, when I read these as 100, that has no significance. You can read it as 100100. In fact, reading it as 100100 may be more appropriate. So, let's say that we know these things on our computer A. To accomplish the area, we would need to do the following. We would need to say load in some data. Let's say we know the location of the length in our main memory, which is our RAM, to be the following memory location: 0100 0001. We then say, okay, we load in our length, we multiply our length using the multiplication binary code, and we know that the width is also in memory as 010010. And finally, we store it in the variable called area. And that's it. This is equivalent to load, multiply, store, length. So load the length multiplied by the width and store that value in area. That's it. And this is not how it will be represented. Obviously, this is just a mnemonic. This is actually how the code will may be written using machine language. You may already notice why we would want to move away from programming in machine language. The programmer not only had to remember the machine language representation of an operation, but also to manipulate the data, the programmer had to remember the location of the data in main memory. Main memory is your RAM. This obviously is not only difficult to remember, but also quite error-prone. We move away from machine language to assembly language. So, assembly language. In assembly language, we use instructions called mnemonics. And let's say we have the following mnemonics. Instead of using 100 to mean load, we just have the mnemonic of load. Instead of 100 to mean multiplication, we have the mnemonic mult. Instead of 1000 that's wrong, to be store, we instead have STOR to mean store. So our following program will be written in the following way. We would say load length multiply with store as area. Now, we also introduce variable names to represent data in assembly. And this, with mnemonics, greatly reduces the need for the developer to remember machine code. Unfortunately, however, things are not that simple. Assembly language is not machine language, and therefore how can a computer execute instructions in assembly language? It cannot execute instructions in machine language directly, which makes sense because LOAD is not equal to a binary code. But we can somehow get that binary code. We need to translate our assembly language to machine language. So we have our .asm file, such as this one. It just has load xxx, multiply yyyy, store zzz. So let's say I have my tutorial.asm. I will use something called an assembler. What an assembler is a program which translates another program written in assembly language to its equivalent program in machine language. So, an assembler takes as input some assembly language and as output produces the machine language equivalent. Let me show you. Make sure we're recording. Great. Nope. We'll start off in assembly, have our code. That code will be fed into the assembler, which will produce the assembly language's equivalent machine code. And this is what will be executed by our computer. Cool. Now, moving from machine language to assembly was great. It made programming easier. However, you as a programmer would still need to think in terms of machine instructions. We had to find a way to make a high-level language that is closer to natural languages such as those spoken by humans. Spanish, English, French, if it exists and it's not government propaganda. So how would we do that? Well, we created programming languages such as COBOL, C, C++, Java, Python, and this thing that people constantly talk about, but I'm sure is also a myth, JavaScript. Disgusting. So let us consider, this is 5, right? High level languages. Let us consider the high level language C++. In C++, for us to calculate our area, all we would need to do is the following. We would say area is equal to length times width. And that's it, assuming all of our variables have been defined. And even as a beginner, you'd probably be able to make out the statement. You'd probably say, okay, I have something called area, and it is equal to whatever length is, preceded by the sign width. And even if you hadn't seen the sign before, you would know it's not a plus, it's not a minus, it's not a divide. It is most probably the multiply sign. And you'll be able to understand and interpret it. Simply put, high-level languages are easy to understand and are self-explanatory. As opposed to us presenting this to a beginner and being like, okay, what is this? Numbers, correct. However, let us again talk about it. We have machine language, which is our lowest language. Above that, we have, let's say, assembly. Above that, we have high-level languages. And again, things are not so simple. High-level languages are not machine languages. And therefore, the computer cannot execute instructions written in any high-level language directly. There's just a problem with that. So what do we do? For high-level languages, such as C++, we use something called a compiler. It too will take in some high-level language. Then we will have our compiler, which is a software program, which will create the machine language equivalent. So what is a compiler? A compiler is a software program which takes input instructions written in a high-level language and translates them into the equivalent machine language. And that's all? No, it's not. Let me go to code blocks. This is just a program that I can use to write software programs in. The first thing I will do is I will include IOStream. This will give me the ability to work with input-output streams. Anything that you see that has the hashtag include is called a preprocessor directive. Just resources that I need. Next, I create a function. It is an integer function called main, and it must return an integer. In this case, it will return 0, just for the heck of it. I will then do a standard console output, so I will write to the console the string hello world. And then I will do a standard end line. So you as a beginner probably have no idea what this means and what that means. You only understand that hello world and that it is going to end up being output somewhere or displayed somewhere. And you would be correct. So this program that I have written is called a source program. Notice it is basically a text file, but it is stored with the extension of .cpp, marking it as a C++ file. The compiler does a few more things in the assembler. It will also check the source code for syntax errors. What's syntax? Syntax is the rules of our language. Equivalent to, say, in English, if we were to write a sentence and forget a full stop, we have a syntax error. We are breaking rules of the language. If the compiler finds no errors in our source code, it will translate it into the equivalent machine language. We will now have something called an object program, which is the machine version of our high-level language. And I need some water. But as I said, things aren't that simple. We next talk about the linker. The linker is not a question, it is a statement. I said this is code blocks, this place where I'm writing my code. Code blocks is called an IDE, or an integrated development environment. And as you can see, it has many bells and whistles all over it. All of these resources are useful for the developer as they aid in development, making things much easier. Within the IDE, we write the code, we compile the code, we can also link and load the code. Typically using a button, in this case the one up here that just says build. Still recording? Yes, okay. Okay, so let's say we compile our program and we have no syntax errors. We will now have an object program. We still need to bring all those useful resources and the code that specifies them from our IDE into our program to produce a final program the CPU can execute. This code resides in a place called a library. The linker is a program that combines object code and library code into an executable code. And that is what a linker is. Next we have the mythical, my dog's barking. She should be fine. Let me actually go check. Someone was cruising for a bruising. Alright, we've covered the linker. Are we done yet? No. We next need to load then executable code or executable program into main memory for execution. And a program called a loader is responsible for this. The purpose of the loader is simply to take our executable code and transfer its contents to the RAM, which is our main memory for execution. Here is the entire process. We will start off in some high-level language such as C++. We will then write code in, say, an editor. The preprocessor will handle all our preprocessor directives. We will then use a compiler to check if our code follows all rules of the language. And if so, we will have a object code. But if not, and we detect some syntax error, we will go back to the editor. And we will repeat this until we get back a syntax error-free code that will be compiled and created into an object code. That object code, which I'll just call object code, will then be transferred into the linker with all the stuff from the library. The linker then links the library contents with the object code and creates an executable code that will be transferred via the loader for execution. And that is the entire thing. And now you understand why, regardless of the language we write code in, how we are able to get output. Finally, we have assembly, or should I say assembler, versus compiler. For one, the input languages. An assembler's input language is only assembly language, and it is machine specific. For the compiler, we have any high-level programming languages, C++, Java, C, whatever. The output language for both an assembler and the compiler is machine code. What about the level of abstraction? Assembler is something that's close to machine language. The compiler is high level of abstraction. Error handling, the assembler has limited error checking, while the compiler has comprehensive error checking. And then we have applications. The assembler typically device drivers, system programming. The compiler, general purpose programming and application development. These, however, are not mutually exclusive. And that is all. I hope this video was insightful.